Hello and welcome to Explaining Rust Analyzer, a video series where we try to understand how Rust Analyzer works one subsystem at a time. So last time we looked at the here expand crate, which dealt with macro expansion. We didn't look at how the actual macro expansion works. We just covered the basic structure we have for identifying files which are either real files or macro expansions. Today we will start looking into the here dev crate, which contains the majority of like named resolution stuff, which I think is probably where the most IDE specific parts are happening. This is the crate where we employ salsa incremental computation in the most important way. So let's start looking into this. Let's open Rust Analyzer, and for the start, let's quickly recap the most important bits of here expand because we will be using them here. So here expand, it defines the HirFileId struct, which identifies any file in the compilation we are working with, and it roughly is defined like this. It is either a real file and then it is use file ID from VFS. Otherwise, this is a result of macro expansion. Which is identified by macro call, which is AstID like morally okay. Oh, let's write this more specifically. So macro expansion identified by the macro call and macro definition, where macro call ID contains file ID and ID, which is, can I just disable this help because it isn't like really helpful. And this is roughly equivalent to text range pointing to actual macro invocation. So yeah, HirFileId, recursive structure, which points either to a real file or to macro expansion, and macro expansion is identified by the macro definition we use to expand this macro, and a textual position of macro call in some specific file. Except that the textual position is stored in a robust way, so that it is not a literal text range, which always changes with every typing, but rather something like, hey, this is like the 7th macro expansion in this file. And given this HirFileId, the main query we have here is parser expand, which takes this file and returns a syntax tree of the parsed syntax node in this file. Okay, now let's finally go to what we are going to cover today, which is here dev crate. This crate is not small and probably be split up into various pieces. Especially, I do think we should really extract name resolution bits out of it. But that's some future work. As usual, the most important module in most of the case of Rust Analyzer is the database module. So here we have def database, which has AstIDMap as a superthread, and like AstIDMap is exactly the thing where we had this parser expand function. And the query we'll be looking today at is this one, file item tree. And I can't believe that like this actually works. So like you see, I can go to definition on this attribute, which is parsed by micro expansion, and actually get to the definition of a thing which it points to. It's like magic. Okay, so anyway, what is item tree? Roughly, this is the secret sauce which makes Rust Analyzer fast, which makes this incremental computation based on Salsar actually deliver adequate performance when doing an IDs. In general, like incremental computation always is just a part of a solution. You cannot just take like something arbitrary, throw incremental computation on it, and be sure that it can be effectively updated under modifications. And the reason for that is that some computations are inherently very brittle. They inherently depend a lot on internal details. Basically, like if you change something and everything else changes, like you have like this avalanche effect where one input affects everything about the output, there is no way you can compute this more effectively than just recomputing from scratch. So in addition to having this generic incremental computation framework, you also need to structure a computation so that you can actually employ incrementality effectively. And especially what you really want to have is an early cutoff optimization. The optimization that, hey, despite some details changing somewhere, you need to be able to reuse most of your computations as is. And this is exactly what item tree is doing. So I guess before we go and look at how this struct of arrays work, let's like just look at the example of what this actually does. So let's create a new example file. And actually, let's do like this. Rust Analyzer debug item tree. And let's start typing something. So on the left, you see kind of like the actual source code. On the right, you see the item tree we get from the source code. Kind of like not exactly the item tree, but like some debug representation which might or might not be sufficiently precise. And the cool thing about this this representation is that if I type something in the body of a function, you see that the stuff on the right does not change. It's only when I introduce new functions it changes, or when I change some like top level attributes of a function. So if I say like pop here and like maybe async, we really should improve our recovery here, because like we shouldn't be interpreting like basically anything at all as a micro invocation. We should at least wait for one here. Okay. You see there's like also slight desugaring here happening. Yeah, but like, yeah, the starting point is that what happens here doesn't matter at all. And that's roughly what makes AD work. Basically, if something in Rust Analyzer depends on an item tree, we know that we don't have to compute the thing as long as item tree stays the same. And as most of the code, and hence most of the edits, actually happen inside function bodies, you know that item tree stays the same and you can reuse most of the things. Okay, so let's look how item tree works. And yeah, you see the item tree for this item tree definition file itself is pretty big. I guess we no longer need this, but as a reminder, like this is how you watch it. This is how you look at this data structure in Rust Analyzer. Okay. By the way, as usual, there's a helpful command at the start of the module which explains, maybe better than I could explain here, what this thing is about. So, item tree. Item tree is built for a single file, which might actually be a real file or a macro file. Actually, that's probably better seen even in the database trait. Yeah, so you see, to get a file item tree, you supply the database with an ID of this file and you get item tree back. This data structure is semanticless. So when you type something like use std collections hash map or something like this, in general, there is two ways you can think about this in the compiler. On the one level, you can think about this as a string of tokens. And you can think about this as like literally this std : collections : hash mapping. On the other hand, you can think about this not as a path which refers to the hash map, but as a hash map itself. So kind of like if the hash map has like some internal ID in the representation, you can look at this as use struct ID 92 as hash map where resolve, like name resolve, this path gives you back. Yeah. So again, you can look at this as a path or as an actual entity this path resolves to. It's very fundamental invariant in item tree that it keeps things in unresolved way. It remembers the whole path, but it doesn't know what this path resolves to. This is very important property because it means that we do not need to recompute item tree if unrelated things change. So for example, if we actually try to store like the result hash map there, that means that if we go to std collections and try to make some edits here, like I don't know, like commenting out the hash module, we would have to redo all other item trees. Because we do not try to resolve at this layer, and because we just store the paths, that means that item tree generally only needs to be recomputed when you edit this exact file. Okay. I guess this gives enough context about what data we store there. So we don't store function bodies. We store kind of like top level things. We store a summary of a file, and we very deliberately do not try to resolve things in this summary. We try to keep the summary dependent only on the text of a file itself. the exact way we represent the summary isn't like too important, but you see that in general we have a bunch of arenas and a reminder. An arena of T is more or less a vector of T. So it's like very thin abstraction. And this arena like includes like all kinds of things you can see in Rust file except bodies. So there's like functions, structs, enums, unions, variants. I think fields should be here as well. Yeah, struct fields, etc., etc., etc. It's instructive to look at the module. So module, for example, contains its name, its visibility, pointer to the IST node which produced the module. As a reminder, we covered file ISTID last time, and it is a pair of... No, it's not a pair. So like AstID is a pair of file ID and an ID within a file, but file AstID is just this later part. It's an ID of a thing in a file, and it is basically the ordinal of this. Sorry. Do we have some nice debug way to show it? Yeah, I don't think we have, but basically if we come back to this example, like this will have AstID of like 0, simply because it's like the first function in the file. We will have a file ISTID of 1, and this will have file ISTID of 2. And because this counts only functions, only top-level things, no matter what we type or delete here, file ISTIDs do not shift, they are stable. So yeah, and the actual items, as if this is an inline module, are stored, well, in this module. As a mod item, and a mod item is basically just an enum of everything which we have here by default. So basically an enum of almost every type here. Okay, so to recap, what this... let me go back to the editor. Oh, what happened here? So to recap, we start with file ID, we get to item tree, which contains a summary of the file. Note, functions which are queries in Rust Analyzer typically have this query suffix. Okay, let's actually correct this name while we are here, because by convention we want the spans to correspond to the name of the file exactly. No, I actually don't want to stage the example, and I don't want to have this module, but this I don't want to have, and I provide a name. And actually, okay, should be merged now. Yeah. Let's just see how this is then implemented. So first of all, this starts with this profile span thing, which I'm not sure if I covered already or not. But basically it shows you this kind of hierarchical profile of the running code, actually. Yeah, you see that like it took us 2 milliseconds to compute item tree for file with ID 3017. It would be cool to actually have actual paths here, but yeah, that's like that's a problem with rationalizer, is that I very deliberately tried to write it in a very pure way where there is like absolutely no way you can actually accidentally read data from the actual hard drive. So all the file paths, everything is abstracted about IDs, and you don't actually know about actual file system, which is very cool for maintaining this pure and reproducible architecture, but is very inconvenient when you actually want to debug things, because yeah, kind of like nobody knows what this file points to. Like, and to clarify, it's like it's possible to fix this, and we actually, I think, fixed that at some point in the past, and then like forgot the fix. Yeah, and you see we also invoke this item tree query for macro files as well. So profile span. And then we cover the function we then we call the function we covered last time, which takes file and parses it into a syntax node. And then, like, if the syntax node is an error which we don't actually understand why it happens, we return an empty item tree, which seems reasonable. Again, like, this is an IDE. If you see an error, you don't want to like abort the whole computation. You just want to say, hey, kind of like, this produced nothing. The error is basically equivalent to user not typing anything at all, and that's reasonable. Then we create hygiene. This is actually interesting, and this is not something we are going to cover right now, and this is not something which is completely rationalized yet. But basically the idea is that I think item tree is actually the layer where we can assign proper hygiene information to identifiers, because in the item tree layer we actually can distinguish between files which are part of macro expansion and files which are originally typed by users, because we want like, if you type foo yourself and you type foo in like macro type foo, you actually want those two textually identical identifiers to be different from the compiler point of view, and that's what hygiene is about, and that's what we should be handled here. Okay. Then we create a context here, which aggregates just a bunch of data we'll be using to construct the item tree, the database itself, the item tree in progress, like this will be like the final result of our lowering, this hygiene we just created, and this source AstIdMap, which we covered last time. Again, like that is the thing which maps this first function, second function, third function IDs to actual source, to actual locations in the source code. So it's a mapping between text ranges which are unstable and numerical IDs which are stable. And for visibility, I have no idea why we need this here, as well as for body context. Okay, so we are lowering a bit of syntax into an item tree. And as usual, like there's like common case, it is like a file, and then there's like a bunch of extra stuff you need to do to handle macros. If this is a file, there might be some top level attributes in the file. Otherwise, we need to lower every item in this file. So hasModule item is an IST trait, which is implemented for everything which contains items. So this is modules, files, and I think block expressions. And the way it works is that we just iterate the items, lower each item, and what we get back is an ID of this item. And again, kind of like why we get is an ID, because item tree essentially is kind of like a whole bunch of vectors. And what we get when we lower an item is an index in this vector, except that there is actually a vector for each type of an item, so like the indexes are also typed. This is like actually like the place where like more interesting aspect of entity component system might come into play, in a sense that you see that we try to be very kind of like we try to be very tight here. For each kind of thing, we have a separate type and a separate vector. So in a net component system, you actually would be more dynamically typed here. You would say, hey, you have like just an item, and an item, a single type, can represent either a struct or a function or a field or a parameter or whatever. And the way you distinguish between them is by like what components they have. So for example, structures and functions would have a name component, but an impl wouldn't have a name component, but an impl would have I don't know, child items component, unlike function or something like that. Anyway, we try to be typed here. Not sure if that's like good or not, because like you see, you sometimes have to write this kind of like walls of matches, which are very boring and very repetitive. On the other hand, it's like not. It feels like it is very repetitive, but actually it's like boring code which you can just like copy paste, and it doesn't cause a lot of problem because it's like boring duplication. Okay, so we lower each item, and I guess let's look. Obviously, we aren't going to cover each and every one of those because they are like most of the same, and there's just like a lot of boring code. Let's cover most interesting one. Let's cover functions. So, lower function, we take an ist with the function, so the actual syntax, the actual like parse text which the user has typed, and return again an ID of this function in the item tree. So as a result of this function, we will push an item into vector which holds functions, and we will return the length of the vector at the time we push this. And it's actually pretty straightforward. So first of all, we lower visibility. And the way we lower visibility is that we handle this force visibility thing, which I don't understand why we need. And otherwise, we just ask for visibility of the function. And this is, again, ist trait. And then we create this raw visibility from ist visibility. And like, why this is called raw visibility? Well, it's exactly the same thing I've talked about in the beginning, in that we want to distinguish between resolved and unresolved code, and that we want to keep item tree at the unresolved layer. So you see here in visibility, we have a module visibility which contains mod path. So this is for things like pub in some cute module. And this mod path contains literally just a vector of names. And a name is basically text. Well, it should have hygiene information, and it will sometime in the future, but not today. Okay. And then, separately, we have visibility somewhere. Yeah. And here, instead of using this path with segments, we use an ID of this module that the path resolves to. So that's why we use raw here. Okay. So, and the way we create visibility from AstID visibility is basically by lowering the path, and the way we lower the path is that we just convert every name to, we convert an AstID name to here's there we convert an AstID name to an actual name. And here we take this AstID name ref and return name ref as name, which creates this name resolve. What does resolve do? Okay, right, because there's this isn't related to name resolution at all, but basically, kind of like here we should plop an hygiene information onto this raw string, which we didn't do. Anyway, that's like probably not too important. Let's go back here. Like basically, like through some like boilerplate, we get a raw visibility which is unresolved visibility. Then again, we convert function name. Here I think we can look into this more closely. So func is an AstID. So func.name is an AstID name. That's like a literal token in the source code with like particular position. And we call asName trait on this. And asName converts this token, which has a particular position in a particular source file, into an abstract representation of a name which is actually devoid of span and devoid of location information. And unless the name is raw, we just create a name from text. And this is like one of the invariants in Rust invariant. It's one of the invariants in Rust Analyzer that HirDef is the only crate which can create names, because like create a name is actually like very complicated operation. You cannot just create a name from text. You need to know the hygiene context. You need to know whether this name comes from the file written by the user or the file generated by the macro, because in those two cases, even though the two names might be textually identical, they might need to resolve two different things. And this is not something we currently do in Rust Analyzer. You see, we just like create this from name, but we prepared the code to properly handle this hygiene in the future by not exposing this API publicly. And in theory, so we have hygiene here. So probably we want to do something like this. We want to pass hygiene to the asName function. I wonder if that actually makes sense to already do it, because it seems like we probably maybe just can do this already. Anyway, basically we convert the AstID name to semantic name. Then we convert function parameters. And again, to get back to the item 3 data, I need to remember this structure. You see that we have a single vector of parameters for all the functions in this item tree. And what function stores internally is just a range of parameters. So this is like basically like a pair of indices which point into this vector and which designate a parameter of this particular function. Actually, while we're at it, it probably made sense for us to look at what are we actually going to create before looking at how we are going to create it. Okay, so we are lowering function, and this is what we are going to get in the end. The function will have name, it will have visibility, it will have generic parameters, it will have ABI, so it's like things like extern C, extern Rust, like the string which is in the codes. It will have parameters, it will have some return type, and again, this return type is essentially a textual representation of a return type. It is not actually semantically resolved in a substitute type. It will have async return type. I wonder, like, why do we? Yeah, it feels strange that we need both red type and async red type. It seems like we should have only one of them. Anyway, and finally, we have well, not finally, we have a pointer to where this thing exists in the source file, which is again is robust against reparsing. And then we will have a bunch of Boolean flags, like whether we have self parameter, body, where like we have default, const, async, and safe keywords, whether this is a function from an external block, and where we have this syntax, which I think is only today applicable to external blocks as well. Okay, so lower function. Yeah, and again, as a terminology, we use lowering when we describe like this operation of going from something unstructured like AST to something more structured like itemg. Okay, so we are lowering parameters. We want to push all the parameters onto that global parameter vector and store an index of parameters. So that's why before we start lowering parameters, we remember the start param index. And then after we lowered parameters, we remember the end param index, and then we say that, hey, params are what we created between those two. And here, yeah, first of all, like we deal with the self parameter, where we need to desugar self syntax into this syntax. And yeah, this is all about self. And then for each parameter, again, we just like convert it unless it is varargs. And I'm wondering why we are not setting the varargs B2B so in Flux here. Probably we do this somewhere else. Yeah, and finally we like push parameter to the global params arena, and then we parse the attributes of this parameter. And that's actually interesting because attributes are written in a more entity component system style, in a sense that every entity can actually have some attributes. And they're like, how do we actually store those? I think there is like some. Okay, yeah, right. Because most of the things do not actually have attributes. We do not want to use a dense array storage here. We want to use a sparse hash map here. Okay, so we've dealt with parameters. Then we lower the return type. Actually, let's take a closer look here. So again, red type is an IST return type. So it is a thing which looks like this, just like a tree of text things. and the type ref is that thing represented in a sort of, well, not so, it's like literally the IST, like the usual enum-based IST, which you would expect to see for a vector. So for that case, what did we have there? Vec I33, I32, and bank. That would be a path type, and path would have a generic argument, and generic arg would be again this type ref, and one of those generic arguments would be the path type, and the never type, and the bank would be the never type, which is named after its stabilization date. Okay. Pum pum pum. If there is no return type specified, then the unit is what the return type is. Finally, if a function is async, we disregard the async return type. Why do we need this colon here? Like, we should just... We should just do this. Okay. Yeah. No. 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 Not sure. Yeah. So sorry, it's painful for me to see one kind of like one bit of data can be trivially derived from, well, not trivially, but could be derived from another bit of data, and we have both of them. Anyway, then we have function ABI, which is again kind of like fix me ABI option syntax token. Yeah, it's probably. It's kind of like we are looking at the last token in the ABI, which is kind of like a sketchy way to do this, but yeah, okay, whatever, whatever gets the job done. Yep, finally, like this last interesting bit, that this function is a syntax node. And syntax nodes, remember their absolute position in the file, so they change every time you type anything. And what we store in item tree, we really don't want to change when you type new comments or something like that. So this is the magical bit where we convert this very fragile syntax node to very durable file ISTID. And yeah, remember that's... Oh, I think that's... Can I just like sort this somehow? Okay. Like this linear lookup is killing me. Okay, so if we have some time left, we will try to replace this linear lookup with hashmap lookup so that it is faster. Let's see if we have time for this. Yeah, and then we fill all the various flags there. And finally, we create an instance of a function. And then we push this function onto the functions array. and return its ID, which we then can convert to the ID of any item, which we then so this returns an ID, which you then can remember as a set of top-level items in this item tree. And this actually has this public accessor. So yeah, I think that's actually covers what item tree is and why we need it. I guess let's quickly view where we use this information. So first of all, the main usage of item tree is to drive name resolution. This is probably something we will be looking next time, but just as a sneak peek, in this dev collector thing, when we create a map which contains for a crate what names are visible in which module, we we are like building that map for this crate. And we start with getting an item tree for the root file of this crate. And then we collect each item from the item tree. So that's one use of item tree. Another use of an item tree is to get more detailed information about things. So if we take a look at the function here, one bit which is conspicuously missing is function body. And indeed, coming back to the example, item tree, the thing is called. Yeah, you see that we don't have body in the item tree. But there is body query, which takes anything with a body, an ID of the thing with the body, like a function, and returns the body. And let's look how it is implemented. So we take the thing with a body, and not only functions have bodies, like constants and statics also has bodies, but let's assume this is a function. First thing we do is that we look up the location of this function in the database. So f is just an ID, and again, we will cover IDs next time when we'll be talking about name resolution, because at this moment, item tree is built per file, so we do not have such a concept as a global ID of a function. We only have a local ID of a function within a particular item tree. This thing is like the future global ID, and what we get here is a sock item log, which contains item tree ID, which is the identifier of which specific item tree we are talking about, with the index inside this specific item tree. So from this location, we actually can get to the source code of this function. Again, you see, like this is ASD. This is again that kind of like non-durable syntax which remembers absolute offsets. And the way it works is I hate traits. So let's try to find out how it works. So it has source trait. Source trait is probably defined for AstIdMap. So let's see. Answer C has source. Yeah, okay. So, AstIdMap. First of all, we have item tree ID, and it presumably can create ours an item tree. And again, that calls this file item tree, which we have been talking about this whole time. So again, start from the location of the thing, we get the tree, which defines the thing. Then we can get AstIdMap, because we also know the name of the file, which defines the thing. And then we parse this whole file to get the whole syntax tree. And now we need to extract from this syntax tree for the whole file just the specific function we are talking about. To do that, we look up the node into the item tree, and again, this is kind of like very generic, but in our case, that would be a function, and I see, okay, I hate traits, I hate macros, and I hate macros which generate traits impulse, because that makes it's impossible to explain what's going on, but yeah, bear with me. So basically, we get this function. We get this struct. And we ask for AstId for this struct. And for function, the AstId would be just this field. And now I am completely lost. We were in the SRC module. Oh, okay, yeah, I'm back. So yeah, we get the AstId. Then from the AstIdMap, we can actually fetch the syntax pointer. Again, AstIdMap does not store the whole syntax tree. It stores only pointers, like the text ranges in the syntax tree. And using the text range, we can actually convert, using this text range, we can start with this root and recursively go down until we fetch the syntax for the function. And let's unwind a bit. We were in the body query. Yeah, so here we get a pair of the syntax of the function together with the file where this syntax is defined. And here we extract the actual block expression as a body. And then we will again convert it to lower representation of the thing. Okay. I guess that's it for today. If I'm feeling like it, I will try to do a short live coding session shortly afterwards about trying to optimize that linear lookup. To recap, Rust Analyzer is based around the notion of HirFileId, which points either to a physical file or a file generated by a macro, and that HirFileId structure is recursive. The main thing you can do with the HirFileId is to parse it into the syntax tree of a file. The problem with just parsing stuff into the syntax tree is that syntax tree is very volatile. Every time you change as little as add in a tiny comment, the whole syntax tree changes because the syntax tree remembers absolute offsets, and all the absolute offsets shift when you add a comment, especially in the beginning of a file. So that's why on top of this raw syntax tree, we have item tree layer, which implements early cutoff optimization, which implements compilation firewall. We take this raw file and extract only the set of top-level items present in this file without bodies, and we are very careful and very diligent about only including IDs and not absolute textual positions in this item tree. This gives us a property that item tree for a file stays mostly the same across most edits. Specifically, only the edits which add new top-level items change item tree. And that means that any functionality in IDE which only depends on item trees and is independent of bodies can be effectively computed incrementally, because most of the times item tree stays the same. I guess that's it. Thank you for listening, and see you next